Thank you, April. And thank you all for sticking around for the last of the last of the last. It's certainly my pleasure to close out this conference, this talk. And my name is Jonathan Gourley, my co-author who's in attendance, Christoph Geis. And this presentation will focus on our method for testing for pyrrhotite in home concrete and rock samples as well, and how we estimate possible safe thresholds of pyrrhotite and assess risk using logistic regression models. So we have worked with many collaborators over the years. Some of you are in the room actually, and we've all focused on pyrrhotite issue, and we hope to continue these collaborations in the future. I do need to especially thank our army of Trinity College undergraduate students who have helped us with everything from sample preparation to analyses and a wide range of research projects related to the issue. We really could not have done all this work without them. So the burning question that I've been asked over the years since we've been doing this is what everyone wants to know: what is the minimum concentration of pyrrhotite in concrete that causes map cracking? We've seen examples of map cracking. This is another homeowner that has a home that is extensively map cracked. Penetrative map cracking is the most obvious symptom of the pyrrhotite reaction. And to have a chance to answer this question, one needs to be able to confidently measure pyrrhotite, ideally by percent weight, to very low concentrations. And this has been proven to be quite challenging, as we're all trying to do similar things here. The method we use at our labs at Trinity to successfully identify and semi-quantify pyrrhotite uses two independent analyses. The first is a thermomagnetic physical test, which takes advantage of pyrrhotite's unique magnetic property. And second, a chemical test of total sulfur using purge and trap chromatography. And so both analyses require a powdered sample, so we end up destroying our samples. We don't get to do strength test stuff, so you don't have to ask that question, because we are not able to do anything other than destroy them and powder them up. And for both analyses, we use the powdered sample. So this is a map of all the 534 homes that we have tested for pyrrhotite in foundations to date across both Connecticut and Massachusetts. This has resulted in about 1,100 concrete samples. Because we test at least 2 cores per home, some we get a few more. Also on this map in the green, which hopefully you can see, oh, laser pointer is in the middle. There we go. The area in green are the bedrock formations that are the sulfur-bearing rocks and have the potential to contain pyrrhotite. Our sampling of homes is definitely biased in the region of northeastern Connecticut here, very close to where the quarry in Wellington, Connecticut, that supplied most of the pyrrhotite-rich aggregate. Although we have tested some homes in other parts of the state, and we're starting to test more in Massachusetts as well, as there seems to be other quarries that are possibly producing aggregate outside of this sort of region of problem area. So back to our method of testing and how it actually works. Pyrrhotite is a solid state solution that has varying amounts of iron in its chemical formula. Higher ratios of iron to sulfur are the hexagonal variety, and these phases are non-magnetic. And the lower ratios of iron to sulfur are monoclinic. And our method can capture both of these varieties because the heating process in the analysis actually converts the hexagonal pyrrhotite to monoclinic pyrrhotite. The magnetic susceptibility parameter, or chi, is derived from the ratio between the sample magnetization and an applied magnetic field. And the value of chi will depend on the different mineralogy within the sample, the abundance of those minerals, the grain sizes and shape, and the sample temperature. So for any two given similar samples, the absolute value of chi may actually vary, but we actually are more interested in this change of magnetism that reflects the relative abundance of a specific magnetic mineral when it is heated up beyond a critical temperature known as the Curie temperature. So for example, here's a result of a thermomagnetic curve of store-bought concrete. Went to Home Depot, picked up some Quick Grit, and it does not contain any pyrrhotite, but does contain magnetite, as most rock aggregate does. As the sample is heated up, magnetic susceptibility remains relatively constant as it goes along, as it heats up here. Oh no. Okay. And then at 580 degrees, there's this rapid decrease in magnetic susceptibility, which is the Curie temperature of magnetite. And that's because the thermal energy overwhelms the magnetism of the sample, and so no more magnetism when it gets too hot, essentially. Pyrrhotite has a unique Curie temperature. It behaves differently as it approaches 300 degrees. So first there's this conversion of hexagonal pyrrhotite to monoclinic pyrrhotite. Then there's this thermal unblocking, and then this drop where at 320 degrees it's reached the Curie temperature of monoclinic pyrrhotite. And it's that drop that we're actually going to try to quantify here and use as a proxy for the abundance of pyrrhotite in the sample. So there are different parts of the curve here that we can analyze, that transition, and then this drop, however, this change in or loss in magnetic susceptibility is what we use and what we report to homeowners when they use our test. So this is the graph that we present in all our reports to every homeowner that asks to use our test for their concrete. And with each report we send out, we highlight an individual specific results. So a homeowner would get their particular results plotted on here. So initially this plot was fairly thin with points. It's filled in through time. On the x-axis is this increasing magnetic susceptibility, and on the y-axis is the total sulfur concentration that we measure using a carbon-nitrogen analyzer, carbon-nitrogen-sulfur analyzer via the purge and trap gas chromatography. So we color code each of these. We color code each of the points. The green points are samples that we have not detected pyrrhotite. So there's, through the thermomagnetic analysis, there's 0 drop, up to what we consider a trace, and I'll explain how we define a trace in a minute. The yellow diamonds are, we detect pyrrhotite, but there's no reported map cracking. When we send our core contractors out, they take pictures, they try to visually see if there's map cracking. This is somewhat subjective because sometimes if basements are completely finished, it's difficult for it to actually, there could be map cracking behind finished walls, but for the most part, with the number of homes we've done so far, it's most of these points are probably correct where they look around and see if they find map cracking. They send the pictures to us too, and we look at them as well. And then all the red circles are pyrrhotite present, and concrete deterioration has been reported to some degree. So if we zoom in to that same graph at the lower end of towards the origin here, you can see that there is this range of values here from 0 to about 5 magnetic susceptibility loss, where we do not see any homes, or have not to date seen any homes with any visible deterioration. Our first instance of this is right here at about 6, and the instances of map cracking increase as concentration increase. But there is this large swath of homes that are low concentration, very low concentration, but do not show signs of any deterioration. And so this magnetic susceptibility value of 5 is essentially our cutoff for what we consider a trace concentration. So what does 5 mean? Like when I tell a homeowner you have 5 magnetic susceptibility, everyone wants to know, what does that mean in terms of concentration? And suppliers want to know what concentration can I have in my aggregate that is low enough that is not going to cause a problem. And so if that 5 level of magnetic susceptibility loss is close to that answer, we need to somehow relate this to a concentration of pyrrhotite in the concrete. And so the first thing we can do is we estimate by looking at the linear relationship between these two parameters. And a magnetic susceptibility loss of 5 equates to 0.2% sulfur, just using the equation of the linear fit. So 0.2% sulfur, total sulfur. But as was discussed in a previous talk too, we need to somehow take out the cement fraction of sulfur as well. And so we can get a handle at this by looking at all the quarry rocks we've looked at. We've had the opportunity to look at about 19 so far quarry samples that are plotted on the same set of axes here. And the difference between the y-intercepts of the two linear fits of the concrete, which we just showed you, and the quarry fit is about 0.13 in difference. And I should mention, I should go back here for a second. This range of sulfur in samples that are pyrrhotite, where we've not detected pyrrhotite, the average concentration works out to 0.14, which is pretty close to 1.72 that was mentioned earlier. So 1.3, if we look at the quarry, oops, too fast. 1.3 between the difference between quarry rocks, which don't have any cement in it, and the concrete. 1.4 is a fairly reasonable concentration to remove from our total sulfur. So if I just do some quick math here, removing the 0.14 from the 0.2% sulfur, which was our total estimate from that 5 magnetic susceptibility drop, get about 0.06 sulfur, and then the relationship between sulfur and pyrrhotite based on the chemical formula of pyrrhotite on average, about pyrrhotite is about 2.5 times the percent weight of sulfur, so multiply 0.06 by 2.5. That gets us to our magic number right now that of 0.15 pyrrhotite by weight. That would equate to or equivalent to that magnetic susceptibility loss of 5. And so this might be close to what you might consider a safe level of pyrrhotite, because we have not seen any deterioration in homes that have concentrations at or below that. And if you look at actual standards that do exist for sulfur and do the conversion between total sulfur that could be available for pyrrhotite, they are pretty close to established standards as well, so that's probably quite reasonable. Okay, so while we maybe have a working threshold concentration below which no map cracking will occur, what about all these homes that are low in pyrrhotite? And these are the homes that are problematic to explain to folks. What about all these homes that are low in pyrrhotite yet don't show any signs of map cracking? Will they develop map cracking? So that's something I don't always have an answer for. Time is definitely going to be a factor. I've got some notes on that too. But concentration of pyrrhotite does appear to be the dominant factor that will determine if deterioration in the form of map cracking will occur. And so we attempt to assess map cracking risk by using a logistic regression model, using the single variable of magnetic susceptibility loss, which is our proxy for pyrrhotite concentration, to predict map cracking based on all the samples we've tested to date. And now that we have about 1,000 samples, the statistics get quite good. And so the way this would work, for example, let's say a concrete tested positive for pyrrhotite and at a value of chi, the magnetic susceptibility loss of 23, the prediction model states that, and this is important how I say this, 14.7% of homes of similar magnetic susceptibility loss were observed to have map cracking at the time of coring. It does not exactly predict the future, but says that, okay, if you have results that are This level of pyrrhotite, based on the magnetic susceptibility loss value, 14.7% of homes that are like that home have map cracking. So it does help put things in context, and but there are other factors going on as well, especially considering things like age and time and how much time has passed. So we have a handle on this too. Pyrrhotite has changed in samples over time, and there's some interesting nuances here in this plot. First, so we're going through time here, back in time. Most homes that we're looking at are post-1980-ish. That's when it's believed that the quarry in Wellington began using material. But what's interesting is that certainly through the 80s and 90s, there are a lot of really high estimations of pyrrhotite in homes, and that tends to taper off. This could be because just naturally the quarry moved away from that material or deliberately moved away from that material. And the other thing too is that we have not seen a home post-2005 that has map cracking, especially at the low concentrations. And this fits into about 15 years-ish worth of time it takes for these homes to develop map cracking. And then if we look at this just slightly differently, but from the same data, and plot the percent of homes that have map cracking of all the samples that have tested positive for pyrrhotite, and put them into bins of 5-year increments, and each one of these are how many homes we're talking about. It's clear that the instances of map cracking have decreased through time. So both the material may have changed and it just hasn't had enough time to develop map cracking. Both those things are certainly at work. So in summary, the rapid test that we've developed determines the presence of pyrrhotite in concrete aggregate and aggregate samples. And combining this thermomagnetic analysis and total sulfur, we predict map cracking can occur in concrete where pyrrhotite is greater than 0.15% by weight. Risk analysis is possible as map cracking probabilities increase as the concentration of pyrrhotite in concrete increases. And the time series data suggests both a decrease in pyrrhotite and about a 15-year delay in the onset of map cracking, especially at lower concentrations. So that's all I got, and we're done for this conference. Thank you.